Here we take a brief look at the SN1, or one of our two major nucleophilic substitution reactions. And this is referred to as SN1 because the rate determining step in this reaction is first order. So the purpose of this reaction is it's used for substitution of leaving groups by a nucleophile. The basic mechanism for a reaction like this is we have some sort of leaving group that leaves. That happens in the first step. That's our rate determining step, or our slow step. That forms a carbocation, and then a nucleophile is able to attack that carbocation to give us the product. The second step here, the addition of the nucleophile, is generally very fast for this reaction because we're reacting with a highly reactive carbocation intermediate. Now, there's a number of factors that you can look at to affect the SN1 reaction. One of the main ones is solvent. In an SN1 reaction, the reaction generally prefers to have a polar protic solvent. Why a polar protic solvent? Well, in general, you want a polar solvent because many of the species involved in an SN1 reaction are polar, and you need that to help the solubility. But also a protic solvent, because a protic solvent helps to solvate the intermediate cation, which stabilizes them. In turn, that lowers the energy of the transition state, and therefore the activation energy. The other primary factor that we look at for an SN1 reaction is the substitution of the electrophile. Because in a reaction like this, we are forming a carbocation, anything that's on the carbon of the leaving group, such as additional carbon groups, or groups that can stabilize a cation by resonance, such as an aromatic ring, or an alkene, any of those can help stabilize the carbocation. The tert-butyl, the first example, helps it very much through inductive stabilization. And so, unless resonance is involved generally, tertiary better than secondary, better than primary. But for the two compounds on the right, in those cases we get resonance involved in terms of stabilization of the carbocation, and those work quite well also. So the main thing we're looking for in an SN1 reaction is our groups that help to stabilize the carbocation. Some of the other factors that are often looked at for SN2 reactions, such as nucleophile and leaving group, we can talk about them briefly here. Leaving group, very similar to SN2. The better the leaving group is, the better the reaction. But the nucleophile has very little impact on the SN2 reaction. Because the nucleophile happens after the rate determining step, it happens in a step that's very favorable. The identity of the nucleophile often has very little effect on the rate of the reaction. Now, one interesting example where we can run into an SN1 reaction is through the use of this compound, sodium nitrite. Sodium nitrite is commonly used as a preservative in meats. And because of the reaction we're going to see, there are limits on the amounts of sodium nitrite that you're allowed to use. Because when sodium nitrite comes in contact with an amine, it can form an intermediate that looks like this, known as a nitrosamine. In the presence of acid or heat, Nitrosamine gets converted to this diazonium ion. This N2 group of the diazonium ion is an excellent leaving group. It leaves, forming a carbocation, which can then have nucleophiles added to it. Well, depending on the situation, what that R group is, where that comes from, as well as what the nucleophiles are, these can cause damage to the cell. And so for this reason, the amount of nitrites that are allowed in meats are limited.